Hi guys, welcome to the fifth episode in our series of videos or series of lectures that are more or less a preparation for my Viva. They're slightly diverging from their initial objective, which was just the Viva, as I'm having quite a lot of ideas on this topic. Trying not to get too lost here, but I think the ideas that we started exploring in the previous lecture were quite interesting and got me thinking for a few days now. So I'd like to continue a bit on that sort of direction without getting too lost, and then linking it back to what we're really supposed to be doing, which is the chapter 4 of our notes. Just double check we're recording. Yeah, that looks good. So on the last lecture, we spoke a bit about the two different philosophies of Wittgenstein, which the philosophies are normally known as the early Wittgenstein and the late Wittgenstein. But for convenience, we just called W1 for the early Wittgenstein and W2 for the late Wittgenstein. And I've mentioned in a sort of a layperson's philosophy kind of way of looking at the world that W1 was a very literal representation of the world. It was a description made up of propositions and very logic driven, which sort of makes sense given that Wittgenstein was a student of Russell and the ideas, the very strong logic ideas come across from there. But then over the remainder of his life, the late Wittgenstein philosophy, or W2 as we're calling it here, emerged, and that's a very different way of looking at the world. Whereas here we deal with formalisms, here we almost always deal with informalisms. In other words, a W1 proposition would be considered nonsense if there was no way to evaluate it to true or false. It was a very sort of mechanical way of looking at the world. In W2, pretty much any sentence that two participants within in a language game can make sense of is considered valid. So it's much more relative to the participants, and the language itself becomes embedded as an expression of the modeling of the world. So the language is just a byproduct of neocortical programming. In effect, the natural language is a way to transfer neocortical programs. And the way that we transfer those neocortical programs is not just via language, but via use. So it's not just that I tell a little kid what an apple is. I show the apple, I touch the apple, and I associate all the different senses, all different modalities with the object. And I build a set of concepts in W2, and those sets of concepts eventually become my language game. So, in a way, the way we perceive reality is largely informed by the language game, because uh, once we learn language, once we bootstrap language within the neocortex, then that becomes the dominant way to perceive the world. We end up creating models and models of models in a conscious way via the language game. In addition to all the other models that exist already in the neocortex that are much lower level and which you can't access. For example, the model of a coffee cup that Hawking talks a lot in his writings. So my general argument, or my sort of the direction I was trying to lead us towards, was that any program P is always going to be made up of this combination of W2 and W1. But this chart is actually a bit misleading because really I think that the portion of W2 of a program is much larger than a portion of W1. Almost always, not always, because of course, if you're making a program about, say, maths, perhaps then things will invert slightly. But even there, I got my doubts because I think whilst maths is a very fundamentally very logical construction, I do think that the way that we end up teaching maths to the neocortex is via the language game. So we end up creating a simplification that has a smaller impedance mismatch with the way the neocortex works. And that's how we understand maths. But let's just not take the example of maths because it's such an edge case. If we think of almost any other program, and I'll include here the program Dogen, which is the program that I'm creating for my PhD. If we take any code from Dogen, I think I just managed to crash GNOME. Oh, here we go. Where are we? Here we go. So if we take Dogen. This is just a random file that I just opened up in Dogen. Um, a lot of times we think of programming as the activity of describing to the computer what it is that we're trying to do. So the series of statements such as for and auto and const and so on. But if we go back to Knuth and we look at literate programming, Knuth defends this idea that actually the program is two things. The program is something, a set of instructions that we're going to give the computer to execute. But more importantly, the program is also a set of ideas that we're trying to transfer from one neocortex to another, and hence the idea of literate programming. So, in other words, think of your program as a work of literature that somebody has to read, and when they read this program, they will go through the concepts and constructs you create in the program, and they will create a model of the program in their brains, and it is against that model that they will be able to code. They will have to, in order to make sense of a program, we don't, in our brains, we don't think of explicit statements in an AST, and we don't look at any of those things. When I think of this program in my head, I visualize an entity like a class, and I visualize methods in this class, and these are concepts that we created, higher level concepts that we created to reduce the impedance mismatch between the neocortex and the Turing architecture. And if you take the domain of model-driven engineering that we got here in Dogen, I have concepts such as transforms and chains. Now, if you remember from my previous lecture, these are domain concepts from the domain of from the problem domain of model-driven engineering. So what I try to do here is I try to recreate or to model the world of model-driven engineering within the source code, such that a domain expert will be able to make sense of these constructs. So clearly, I'm also here. I'm definitely in the domain of I'm the region of W2, because the computer doesn't particularly care that I call my class model to text chain. That's irrelevant from a Turing perspective. It's just a label. But from a W2 perspective, it is actually really, really relevant. In fact, it's probably the only thing that's relevant in all these constructs is that I'm creating an entity which is a transform, and it's a composite transform. And the role of that entity is to convert a model to text. This information that I'm supplying to the programmer, to the other programmer that will read this code in the future, it could be myself, is literally a set of models that are encoded in the code. So there's this dimensionality that's hidden. Well, it's not hidden per se. That's why we ended up with higher level languages. But I think the important thing to remember is always this: the code is always composed of two things: a set of ideas that we are trying to model, which are W2 ideas, and these set of ideas are very, very difficult to formalize because they belong really in this W2 space. And then there's the limitation of the construct of the language in which we're trying to express those ideas. And that language is the W1 construct because that's what the Turing architecture understands. Um, so when we try to transfer this to model-driven engineering, then, if we go back to our example here, what model-driven engineering is proposing is that we start transferring some of the concepts that we are modeling at inside of the W2 space of a program. We're trying to transfer those concepts into W1 space. This is what it means to create a DSL. It basically means that you're losing the ability to have this loose way to describe things, and we now have a strict formal way to describe things instead. Um, so as I mentioned before, instead of having a construct like class option, we'd start with the keyword option, which we introduce specifically for the domain of financial products, and so on, such that you can't express anything other than financial products because the DSL is constrained to that domain. Now you can easily imagine what kind of problems we're going to end up here. This and I think this is where I think it's definitely worthwhile writing a paper on this, because I think that this is a fundamental limitation of model-driven engineering, that because the world of W2 moves so quickly, because the language games are dynamic and they keep on happening over time, and terms evolve very, very rapidly, the more you encode these terms in the rigid structure of the W1 world, the more problems you're going to have to get them to update in tandem with the ever-changing reality of the W2 world. And that's, I think, one of the biggest problems that model-driven engineering has. Uh, First, um, it's very difficult to take all these ideas that live in W1 space, in W2 space, and convert them into a strict formal representation. And second, when you do that, you freeze time, just like you freeze time when you write a program. Um, every time I extend Dogen, every time I modify Dogen, I notice that my understanding of domain-driven engineering changes, because as I try to encode something in source code, I need to think about it quite deeply, and that thinking results in me understanding the concept differently, which means that almost as soon as I write some code, as soon as I end up representing something in code, I figure out that actually that's not the right way to model it. And this has happened many, many times over the course of 10 years. The more I learn about the problem domain, the more I figure out that there's some fundamental modeling error in the way we're describing something, which then results in me having to rewrite the code and rethink the concept. And I don't think this is a bug. I think this is a feature. This is exactly what it is that happens when you try to program in a domain. You the domain, again, we have to go back a bit to philosophy. So there's these two notions um, of how the world works. There's sort of the Platonic notion of the world, in which there is a perfect representation of every single concept that you may have, and this perfect representation exists at a higher level, somewhere that we can't normally reach. And then when we translate these perfect representations to our world, they become imperfect. And the purpose of knowledge is to try to get as close as possible to this limiting definition that exists somewhere. And in that sense, we believe in sort of a Platonic ideal. And then there's the other way of looking at the world, where there is no such Platonic definition. And I think this is very much what Wittgenstein says. Um, Instead of a Platonic definition, there is a dynamic definition. All there is our conversations and our ideas and our words and our thoughts and whatever it is that we communicate with each other. And we learn about certain concept by learning about that concept. It is the very process of learning and discussing and thinking about it and debating it that creates the concept. And that process is ever evolving, never stops. So therefore, you would never find the perfect definition of anything. And in a way, you could say that to programming languages as well. I mean, one reason why there's so many programming languages is exactly because there's so many ways of creating a higher level representation of a program in a way that's more compatible with the way the neocortex works, as well as the process of having millions upon millions of lines of code that need to be maintained. That's why we have languages like Rust. That's why we have languages like Haskell, Prolog, completely different approaches to the problem domain. It isn't the fact, my personal opinion, it isn't the fact that there is such a thing as a perfect programming language in a Platonic space. It is the fact that we need to construct many, many languages, and we need to use them in practice with many, many sample programs until we realize what are the pros and cons of each language, and until we figure out which languages we think are better for the job. But just like the language game, this is not something we can't evaluate this in a scientific manner. It is not possible for you to come up with um, a method of evaluation of, say, Rust versus C++, which will enable you to determine which language is the best. It will always be something that will be very difficult to quantify. Um, and the reason why is because you can't create a proper scientific experiment. You can't create a scientific experiment that compares the exact same process twice. So, for instance, let's imagine that you attempt to create a program in C++ and create a program in Rust, and then you try to evaluate which program is the best. The person doing the programming will have a great impact on the quality of the code written. If you find a person that has never written Rust and a person that has written, say, C++ for all their lives, it is very likely that the program from a C++ person will be much better. But even if you find two people that are of all both mastered each language, you still have the difficulty that each of them may know more about the specific problem domain that you're targeting. And the very fact that they may write the program once and then twice and then three times will also have an impact in the way the program is written. So it is perhaps possible to create trivial examples, such as a sorting algorithm or something as trivial as that, in two different languages and then do some kind of cursory evaluation. But that's not really that doesn't translate well to scaling that to any program. And in fact, one of the things I try to do in my notes is I try to make an argument. I try to make an argument that any kind of I think I've actually left that to my thesis now. But the fundamental argument that I was trying to make was that any kind of argument such as um, A is better than B, or proving that A is better than B, it is actually almost impossible to do in the context of software engineering, because we don't have the reproducibility of science. Um, Software engineering requires you to understand the problem domain, and the very attempt at understanding the problem domain modifies the experiment. So you can't have the separation that you have, for example, in physics, where observe. Of course, you could say that this is not perfect in physics either, but let's just imagine the simple version of physics. In normal non-quantum mechanics kind of world, observing a phenomena from a scientific perspective does not affect the phenomena itself. That is part of the training that you get when you're trying to do an experiment, is to try to make sure that your experiment is not changing the phenomena that you're trying to experiment with. But in computer science, that is not possible, just like it is not possible with economics. Because once you try to do any experiment that involves humans, and where the humans are the participants of that experiment, it is very difficult for you not to modify the behavior of the humans that are being experimented upon. It's also not very easy to create conditions that are um, considered identical in two completely different setups. So for you to make a statement such as Java is better than C sharp in a scientific way, it would require this ability to disassociate the experiment from the way you are conducting the object of the experiment from the way you're conducting the experiment. And this is a property that I believe extends to almost everything within computer science, within software engineering, because, and the reason why, of course, is the W1 W2 dichotomy all over again. The problem is most of the time you spend stuck in W2 space, and the W2 space is relative. It's relative to the people in the space. It's relative to your understanding. It's relative to thinking. It's relative to the concepts that you make, and so therefore it will never be possible for you to create something that's independent, because the very notion of thinking about W2 changes W2. Um, so anyway, all of this is to make a very complex argument, but I think that with this we start to understand where the limits of model-driven engineering are going to come from, and that is you won't be able to create some kind of generic solution to model-driven engineering, because to do so would more or less be to create a neocortex. So instead, you have to have specialized solutions, and these specialized solutions are always going to have a limitation, and that limitation is that you freeze time, and if you freeze your understanding of something. And sadly, because a lot of the things we're interested in modeling in model-driven engineering are W2 concepts, that is not a useful thing because the world keeps moving. So now, having said all of that, hopefully this all makes sense. We'll now go back, and before we go on, let's just have a look at time. So 18 minutes. So today's going to be a short one. We'll just try to finish this chapter 4 so we can move on this. So what we're going to do now is we're going to discuss a few concepts that are very relevant to MASD, and we're going to talk a little bit about. So the ideas that we want to discuss are concepts that are part of the body of knowledge of model-driven engineering. They're also part of normal software engineering, but they're more relevant in terms of model-driven engineering, because we try to clarify all these notions in order to understand what the modeling process is supposed to be about. And the two elements that I would like to start with is the problem space and the solution space. So pretty much everyone knows what the problem space is, or the problem domain. So the problem domain is the thing that you're trying to develop for. So in going towards our ideas that we just mentioned a second ago of a program being divided into W1 and W2, you can think of the problem space as a set of entities they're going to end up modeling, because they represent these W2 concepts they're inherited from natural language, and you're trying to represent that inside of the program. So that's your problem space. And the solution space is the set of things you're going to use in order to create the solution. So, for instance, the programming languages, the compilers, the operative system, everything you need in order to create the software system. And you can imagine conceptually that there's this boundary between the problem space and the solution space. Um, and your job as a software engineer is to somehow move from problem space towards solution space. And as you do that, something interesting happens, which is you start to lower the abstraction level. Um, so let's just look at our image that we used previously. So you can imagine that you may start. This is a sort of an old way of doing things, but even in Agile, conceptually, you can imagine that you do something like this. You start by observing phenomena inside of the problem space, and that set of observations will eventually come up, will be condensed in a set of requirements that capture the subset of the problem space you're interested in. Now, these requirements don't necessarily need to be a complete description of all the phenomena that you're interested in. They just need to be sufficient so that it can pass on from this step to the next step. And so, as you gather these requirements, you start to perform some kind of analysis on those requirements. And the analysis then condensed in some form of architecture. In other words, maybe a set of services, maybe a database. You start to think of terms of how it is that we're going to condense all of those requirements. Eventually, you're going to end up designing a set of components. This could be, for example, a set of classes or maybe some high-level construct. And sooner or later, that is going to have to be represented as source code in any programming language of your choice. And as you start to see this sort of descent, we start to get closer and closer to the solution space. But this is a gradient. You never at one space in particular. These are just concepts that we create. This is just a model of the software engineering process that helps us visualize what it is that we're doing. But this is firmly in W2 space. We are talking about a set of things that can't be formalized. I mean, you could possibly formalize the nature of the software development process, and that's, I guess, what people try to do with waterfall. But we all reach the conclusion that that's a terrible idea. It's much better to have this in a flexible manner and a very dynamic manner in order to react at the changes that are happening at this end, and think of this as a cycle. But in this this MDE world, we're thinking of the use of modeling languages at all levels of this descent. The idea would be that perhaps there is a modeling language for modeling requirements, perhaps there's a modeling language for analysis, perhaps there's a modeling language for architecture, and so on, all the way to the source code. Now, this may seem a very strange thing to do, but in a way, we kind of do something similar to this. Because if you think about it, you probably are going to take something like a UML diagram. I mean, UML is probably not the most used technology these days, but some form of diagram representing the software architecture of your system. And you're going to have lots of whiteboarding sessions discussing that diagram backwards and forwards until there's some kind of agreement. So you can think of that as your software team is playing a language game inside of the domain-driven space, trying to debate and formalize the model, your understanding of the problem domain, and trying to formalize the solution for how you're going to model that problem domain. Of course, all of this is informal, so you can't just translate that directly to source code via some tooling, because you're firmly in the W2 world in such a way that it's not possible to do that. But you can imagine that if you were to create a UML diagram that was actually formal of that architecture, you could then translate that to source code. At least from a structural perspective. Behavior, of course, will be another story, but from a structural perspective. So this process that we can conceive of going from each of these layers or each of these steps and going downwards to source code is called model cascading, because you're basically going from one model designed for a certain step of the process to another model, and each model is specialized in that particular point in the process. And as you're cascading, you're transferring information and converting it from one representation to another. And these models are being refined. So this is a very, very simple topology, but you can imagine very, very complex or more complex topologies, because it is not just the case that you make changes that requirements end and those changes propagate downstream. It could also be the case that you make a change at any of these ends, like middle even. You could change the architecture, and that could have an impact on the requirements, and that certainly would have an impact on the source code. So the topology that we're going to use for model cascading is not necessarily a linear, nice topology like this one. It could be much more complex than that. And of course, you can imagine that the purpose of this is at some point to do full or partial code generation. Like I said, behavior is not very easy to model, so that's why partial code generation makes sense. Now, if you think about the solution space, it is useful to also model the solution space. I'm not quite sure we discussed this already. I don't think we have. So the solution space, well, as programmers, of course, we have all sorts of names for programming language and so on. But if you think about it, that's kind of a not a very taxonomic. It is a non-taxonomic organization of the solution space. There is some taxonomy, of course. If I say programming languages, I'm talking about a group of all possible programming languages, and so on. But what the MD people spend time doing is they spend time redefining and refining the taxonomy for terms that are useful for model-driven engineering. So two very important concepts are technical spaces and platforms. So a technical space is a set of well, let's actually read the Kurtev definition, because I think it's a good one. So a technological space is a working context with a set of associated concepts, body of knowledge, tools, required skills, and possibilities. And then Menz and Van Gorp subsequently added that a technical space is determined by the meta model that is used at the M3 level. So what they're really trying to say here, I think, if you were to translate to the software engineer vernacular, is they're talking about something like, say, C++ or XML or Java or something like that. Because each of these has their own meta model, and each of these has their own set of, a body of knowledge. For example, the idioms that we apply when using Java, a set of concepts, all the books that come with it, all the tooling, and so on. And they're trying to say that when we talk about the Java, the language, really, we don't really mean Java, the language. We mean Java, the technical space. Because if I say Ant, or if I say JUnit or something like that, even though these are old things probably, but any of Maven, I guess, all these things should really be part of the Java technical space. And of course, just like there is Java technical space, there are many other technical spaces. And then the second sort of related concept to technical space is the concept of a platform. Actually, before we do that, let's just look a little bit at Bézivant. Bézivant is the interesting thing that is, I mean, why would you come up with the concept of technical space? We've been living with the notion of a language like Java, and that has not been a problem, right? So what they're trying to say is this. We spend a lot of time trying to transfer information from one technical space to another. And it would be nice if one was to model technical spaces in a more formal way. Perhaps that would allow us to transfer information across technical spaces in an automated sort of way. And now, of course, you start to see how this links back to our model cascading and so on. Because what they're trying to say here is, in order for you to start to automate these processes, there has to be a certain set of formality surrounding the technical space. And there's always going to be the need to, because no, as I said before, it's not possible for one programming language to be formally declared superior to another. There's always going to be multiple approaches to a problem. We're always going to end up having to go from one space to another. As an example, you may want to use XML, but you don't have to use XML. You could use JSON. But if you do use XML, you are then going to straddle between Java and XML, because in XML you're going to have schemas, you're going to have all of the paraphernalia that comes along with the XML technical space, and which is distinct from the Java technical space. And the reason why is because XML specializes in a specific set of of a problem domain, and Java specializes in a different subset of the domain. And so, most of the time, when you create a solution, you're always going to end up straddling multiple solution space, technical spaces. Um, and so once you think of this as spaces, you start to think of projections, and a projection is this transform, um, translation between spaces that I mentioned before. The idea is that you may want to inject or extract information from one technical space to another. So to make this simple, imagine, for instance, that you're in the technical space of XML. Uh, Perhaps it would be really nice to be able to convert an XML schema to a set of classes in Java. So in this sense, we're doing a projection from the XML space, creating a set of extractors, and then we're going to create a set of injectors that then convert the information extracted over to the Java technical space. Um, Now, of course, in this I try to do a lot in my notes. These concepts are all very useful, but they are very imprecise. In effect, we are really very much at the top of the W2 space here. These concepts are language games that we need to play inside of MD in order to make sense of all these concepts. These are not formal concepts, but they're useful because, as you can see already, we're building a vocabulary of functionality that allows us to model these concepts. Um, then we reach the second vital concept inside of the solution space, which is the concept of platforms. Now, again, we're going to have exactly the same problem. It's very difficult to say what a platform is. I mean, if I say something like, say, Linux, or if I say something like JVM, or any of these concepts, you will immediately say, okay, that could be a platform. I can understand why you'd say that's a platform. But it's very difficult to define formally what it is that we mean by a platform. However, intuitively, all programmers know when you're targeting the CLR, you can think of it as a platform. When you're targeting the JVM, you can think of it as a platform. When you're targeting Linux, you can think of it as a platform. The notion of platform, as we understand it in MD, goes further than that because even something like a library can be thought of as a platform because what the platform gives you is the ability to raise the abstraction level. So instead of starting from, say, the C++ based language, once you start with a set of libraries in C++, you are raising your abstraction level, enabling you to think closer to the domain rather than at the lower level that library thinks. So the platform is it's just this series of abstractions that we create from a very low level abstraction, like, say, for example, the JVM, to a much higher level of abstraction that are constructed inside of a technical space. Um, and and this is important from a model-driven engineering perspective because the more um, semantically rich and domain-specific, to quote these terms that I regard here, the higher the level of the platform, the easier it is to then build on top of that some kind of modeling language. This may not be obvious, so let me try to explain what I mean by this. Nothing would stop you from taking a UML model and converting that to assembler. You could do that, in fact, to machine code. You could just translate that directly. However, it will be much, much harder to do that than it would be to convert the UML model to, say, C Sharp or Java. So you can think of C Sharp or Java as a platform that is raising your abstraction level. Uh, that makes the modeling task much easier because it's much easier to create a simple text file from a UML diagram that represents valid C++ or Java constructs than it is to create um, machine code. It is not impossible, but it is much harder because now you're taking on all the responsibilities that compilers have already taken on. And the exact same thing happens with libraries. You could, of course, translate, say, the notion of a vector or any mathematical concept. You could translate that into C++ code that models that concept. Or you could instantiate a library, like, say, for example, in the domain of linear algebra. You can instantiate code in a library that already exists. And model-driven engineering benefits a lot from this raising of the abstraction level because it enables you to focus on the mapping and on the DSL that you use for modeling rather than on the implementation. So platforms are very, very important. Um, and and this dilemma that I just explained there is an illustration of what's called the problem implementation gap. And the problem implementation gap is this idea that the bigger the gap between the entities that you're modeling within the problem domain and the implementation domain, the bigger this gap, the more difficult it becomes to bridge the gap. And that's more or less the process I described just there. It is much harder for you to create machine code from UML diagram by many orders of magnitude than it is to create, say, C++ code. Uh, and in the same way, if you are trying to model financial entities, it will be much harder for you to create uh, all of the C++ code required to model those entities than it would be to just reuse, say, something like quantlib that already does all the hard work for you and defines all those entities already. So it'll be almost trivial for you to, it'll be trivial in comparison for you to create the mapping between um, entities in the DSL created for the financial domain and a C++ source code implementation that uses quantlib versus you creating all that from scratch. Um, and so at this point, we then enter the domain of the PSMs and PIMs. And so this idea then is that we mentioned before that a model could be platform specific or platform independent. I'm not sure if we mentioned this before, but now that we've introduced the notion of a platform, it should be obvious or more obvious what we mean by platform independent and platform specific. If you've got a model that only focuses on domain concepts and is not related directly to the specific platform that is going to implement those concepts, then one can say that model is platform independent. However, at some point, you're going to end up with a model that's platform specific because you need to somehow instantiate the specific concepts that you're going to end up translating to in the source code. So, in other words, somewhere in your code, you're going to have a model that says, I would like my code to be expressed as C++. And once you do that, then you need to know um, how how the types get mapped between a platform independent model and a platform specific model. So, for instance, is this a string? Is this a double? So you need to create this translation layer. So whether explicitly or implicitly, you're always going to end up with a platform-specific model. This is just part of the process of the cascading that we mentioned before. There's no avoiding that. Um, and of course, it is not this mapping that I just described here is by no means trivial, particularly if you imagine that the platform independent model is created in the DSL of your own making. So presumably, it means that you have to worry about this description and mapping for every time you create a DSL. I mean, of course, there's tools for all these, but I'm just trying to talk about the generic problem. Um, and this mapping could, of course, be hidden and hard coded in source code, which is what we do in certain cases in Dogen. Not always, but I think that's more or less about it because I think we're running out of time slightly. Let's see. Yeah. Okay, so then just to summarize what we've done here, then we spoke a little bit about the dichotomy that we have in any program that must straddle between W2 and W1 space, and the programmers would always live in W2 space and spend all their time trying to do this mapping. We then started to talk about the modeling that we do of the software engineering domain itself within model-driven engineering, because it's very helpful for us in order to understand how the modeling will work. In order to construct, this sounds a little bit confusing, but in order to construct models of the problem space, we need to first understand how those models are going to work in a pipeline of the software engineering world. So to do that, we need to have a model of the software engineering world. And so we then described a couple of core entities on that model of the software engineering world. And we also described the limitations of those two core entities, platforms and technical spaces. Um, these two entities are key to almost all the work that MASD will do, and we will explain later how these integrate with MASD. But I think for this lecture, that's probably enough. I think. Okay, thanks for watching.